Okay, so let's go. So hello everyone. We are very happy to have Kristan Jensen today from the University of Victoria, and he's going to talk about wormholes and black holes microstates in AdS CFT. So and he agreed also to have like 10 minutes of discussion afterwards. So if you have any more questions after the talk, please. And now I leave it to Kristan.
Okay, well, thank you so much for the invitation. It would be infinitely nicer to see you all in the flesh, but this is the way of things. Yeah, let's get started. So this talk today is largely based on a paper that I wrote with an excellent postdoc, Jordan Kotler, that appeared last week on arXiv. It's this one right here. Although there's a couple of earlier works that were sort of essential in the story and in setting up the story that I would also, if you're interested in these things, I would suggest taking a look at. Right, so let's get to it. 2 comments to start. I'm going to try to give something that is an analog of a Blackboard talk. So I'll just try to go slow and on the tablet here. At any point, please ask questions. And the second comment is that this is a talk about holography and AdS CFT, and I'll be, referring to these concepts throughout. So it's a little bit more technical than an average seminar in particle theory. But do ask questions if you have any along the way. Right, so let's get started. The subjects that I have in mind today in this talk are so-called holographic CFTs, that is, conformal field theories that have a holographic dual. And these theories inevitably have something like a large n parameter, like a rank of a gauge group that is very, very large, and are also at strong coupling. In such a way that their physics is nicely encoded by that of quantum gravity in AdS space-time in higher dimension. And one very robust result that was realized early on, immediately in the early days of the AdS CFT correspondence, is that if we put these such a holographic CFT on a space like a sphere, put it on a spatial sphere, so on time cross a sphere. So I'm going to take the convention that the CFT is d-dimensional, and if you put it on a space of this sort, then the Hilbert space of the theory has a nice, there's a nice picture that you can draw. So let's consider the density of states as a function of energy on the sphere. And using the usual operator state correspondence in CFT, this maps to the spectrum of local operators in flat space. So this is a natural thing to study. What you get is a bunch of light operators. So you get like a Dirac comb where there's a lot of light operators. And what do I mean by light? I mean operators who states whose energies are either order 1, or order the coupling constant, that's relevant for a large n theory, the 't Hooft coupling, say square root, if we're talking about n equals 4, order n, things that are light states, lighter states anyway. In the canonical examples of AdS CFT, these states typically have an energy that is protected by symmetry, by the superconformal algebra. Well, there's those states, and then a generic state in the CFT has a very, very high energy. It's pushed off way over here, and there's an enormous number of them, much more so compared to the spectrum of light operators. And the spectrum of one of these CFTs is discrete, And so the density of states is some complicated Dirac comb where there's states in a fixed energy. There's an enormous number of states over here. If you were to coarse grain over a small window, there's order e to the n squared states over here with a level spacing of order e to the minus n squared. So there's just a huge number. That's a generic state in the model. If it's unprotected, it's completely non-BPS, generic state in the theory, it's going to have an enormous energy, and it'll be over here. And what are these states in a holographic dual? What do these states correspond to in AdS spacetime? Well, the light states correspond to things like fluctuations of supergravity modes, or strings in AdS, or branes. And what do the generic states correspond to? These things where there's a huge number of them, well, they correspond to black hole microstates. And the way that you can be concrete about this is in CFT, you could imagine coarse graining by a little bit. And then this Dirac comb in of these heavy states is going to have some continuous density of states that you would get upon coarse graining that's huge, that's order e to the n squared. Whereas the light operators, there's not enough of them to coarse grain into something continuous. And this continuous density of heavy states, well, what is this? Well, this is what you extract from black hole thermodynamics upon going from fixed temperature to fixed energy. You extract density of states. And what is the density of states that you get? Well, you get this, something like this blue curve, a coarse-grained approximation to the spectrum of heavy states in the theory. So that's what you get. And the thing is that in AdS CFT, the exact spectrum of black hole microstates, what are the exact energy levels, what are the, where do they sit precisely, is a deeply non-perturbative question that's completely inaccessible in the year of our Lord 2021. Mostly on account of these energy level differences. They're just too small to resolve at any loop order in gravity. It's deeply non-perturbative. However, the thing that is readily accessible is the coarse-grained version of the density of states. That's something that's computable, and in fact, it's computable to leading order in classical Euclidean gravity. Just the usual old story with black hole thermodynamics. And well, what's the point of today's talk? The point of today's talk is that, if you will, I would like to advocate for another entry in the dictionary between Euclidean gravity and the properties of black hole microstates. The particular property that I'm going to be discussing today is not related, though, to the density of states per se, but to level spacings. So I'm going to present evidence for something that's called present evidence for long range level repulsion suitably coarse-grained, like the black hole density of states, that is that of the spectrum of black hole microstates in theories with a holographic dual, that's encoded by Euclidean wormholes. So encoded by another computation in Euclidean gravity. Okay, so how do we get here? Well, and I guess I should say, yeah, one little comment before going on. Just to say where we're going a little bit with this. I'm going to be working in a way where for most of the talk, I talk about gravity in Einstein gravity with cosmological constant in AdS spacetime. But one of the consequences of the most recent paper is that we can embed this story into full-fledged, 10D or 11D supergravity, and therefore into proper AdS CFT. And the other consequence of this is that because we arrive at a way to talk about wormholes in AdS, well, these wormholes, I'll present evidence that they encode something very nice, level repulsion, which is something that one expects, as I'll review here shortly. However, they also come at a cost. In particular, they introduce something called, that people have been talking about lately, called a factorization paradox. So they encode something nice, but they bring problems, and we'll discuss this at the end.
Can I ask a question, Kristan?
Yeah, of course.
So regarding the spectrum that you draw,
yeah.
So the light operators with the order 1 dimension or energy of the state. So these are the Kaluza. If I'm referring about AdS 5 cross S5, the classic example. So those are Kaluza-Klein modes on S5. So we know everything about those.
Yep.
And then there are the states with order square root of lambda. So in particular, those dimensions, I mean, asymptotically large n does not depend any longer on n. I mean, it depends a little bit, but the order is fixed. So there has been a lot of work with on computing the spectrum using integrability.
Right.
So do you know whether, I'm not familiar with those techniques, but do you know whether one can obtain information, maybe confirmation about what you said about the spectrum using integrability?
Yeah, I mean, this is what I had in mind. The classic example is the Konishi operator, the SO6 and the lightest SO6 invariant scalar in n equals 4. So that one, its dimension, I think that operator is the dimension of that operator. It's dual to a stringy mode in AdS, and its operator dimension is computed by the integrability people in a way that I've never sat down to properly understand. But how to say, there are some additional symmetries of the problem that emerge when computing the spectrum of such modes at infinite n and any lambda, and that's I know that's roughly how they do this. But there's other, there's even heavier states than the strings whose dimensions are determined by symmetry to leading order in n at large n, like certain branes in AdS, for instance.
Yes, but what I meant is, so the argument you gave was, okay, you can compute this coarse-grained version essentially classically. You compute black hole solutions and black hole thermodynamics and so on. But can you get information about level spacing and the density of states using integrability? Or?
Not to my knowledge, actually. Not to my knowledge. I think the sort of you need these extra symmetries. You need this Yangian symmetry that emerges at infinite n. And as far as I know, that doesn't constrain the black hole spectrum.
Okay.
Okay. So the plan for the talk is the rest of the talk is as follows. Oh, when it does this. So the plan for the rest of the talk is I want to talk about what we should expect in the level statistics, because that's something that condensed matter theorists that are used to chaotic many-body systems have thought a lot about, but maybe less so for us high-energy theorists. And then I'll talk about wormholes in AdS and how to arrive at them and how to see the connection with level statistics. And probably by that point, I won't have any more time. So we'll probably conclude there. But if we did have a little bit more time, I would talk about embedding into full AdS CFT, where one can also talk about new physical effects in the context of these wormholes, including prospects for brane nucleation. Yeah. 5, 6 in the morning, my energy level is just not high enough to be able to take us through all this in an hour, but okay, so be it. Okay, so what should we expect? Something that I have learned recently from my collaborator is that, sorry about this, every time I put my palm on here, it's becoming large, is that there are some robust facts that they've taken on the status of lore in the many-body quantum mechanics community that they expect for many systems concerning the level statistics. So these, if you will, these are fairly generic, robust, universal features of complicated many-body systems. And all of this goes back all the way to work of Wigner and Dyson back in the 60s and 70s, where it sort of started. And the first one, oh, and when I say robust and universal, I mean, things like spin chains, quantum mechanical problems like a particle in a stadium, whose classical limit would be a classical chaotic system. Just roughly speaking, many lattice models. Although, as I understand it, there's not as much work in this setting on lattice gauge theories, but so be it. So the first thing that's very robust is something called nearest neighbor level repulsion. And what is that? Well, the baby version of this is something that you see in an undergraduate quantum mechanics class when you look at sort of the spectrum of a generic 2x2 Hamiltonian, and you see that nature abhors degeneracy. And unless there's fine tuning, the energy levels of some Hamiltonian are non-degenerate, unless there's a symmetry reason why they should be. And this can be quantified if you take the spectrum of some complicated Hamiltonian with a discrete spectrum, and if you you order the states according to energies, and then you see what are the energy differences between adjacent states. And then if you, you collect that list of energy differences, and then you order that list by the size of the energy difference, and then you coarse grain a little bit by binning basically, then what you get is a plot where, let's call this axis S, this is the energy difference, and this is how many states that you have upon a little bit of binning with those, how many levels you have with that difference. There's some, this thing tends to 0. And for generic Hamiltonian, this depends on sort of the discrete symmetries of the problem, but for generic Hamiltonian, this grows as energy level difference squared near 0. And what this is saying is that levels don't like to have exactly the same energy. They like to have some small amount of energy difference. This is a very robust and universal result. The thing is that, you know, you might ask, could we see such a phenomenon in gravity with black holes and AdS? And maybe someday, probably not now, because when the nearest neighbor level repulsion is a question about the very, 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 very fine-grained level statistics about this, these order, the sort of scales involved here would be of order e to the minus n squared, say, for n equals 4 super Yang mills. And that's just too small to probe. That would correspond to energy differences of that sort correspond to time scales that you might study in AdS of order e to the n squared. Just very long. So there's another thing, though, that is robust, and it's this, very roughly speaking, it's the following idea. You know, if nearest neighbors' energy eigenstates repel each other by a little bit, then that means that there's some repulsion over macroscopic distances in the spectrum. You take two states of some energy, and they also will repel each other, even if there's some finite distance away in energy. But the interaction's a little bit floppier. It's not quite as rigid as the very short-range repulsion. This goes by the moniker of long-range level repulsion. And the fact that it's there is a universal feature of many, many body quantum systems. But there's another quantitative feature that is, it's not universal per se, but there's a lot of evidence for it, which is that if you were, how to say, that if you look at the 2-point function of eigenvalues suitably coarse-grained, let's call that rho 2, depends on 2 energies, that this goes like minus number divided by the difference in energies squared, even when those energies are, you know, in, not very close together. And the minus sign is encoding the repulsion.
This is what you get from random matrix, no? Usually.
Yeah. This is one of the main results of this field of many body quantum chaos, is that you get exactly this result in random matrix theory. Random matrix theory makes a prediction for the coefficient that's there. Now, this is hard to, this level repulsion, this long range level repulsion is something that is a better target that you could aim for in gravity. But even so, it's a little bit, it's a little bit hard to try to access. There's another feature of it that is more readily accessible, from something called spectral form factor.
Sorry, can you mentioned random matrix theory for your point number one. This then, yeah, at small s, this, well, or at large s as well, there's a prediction, right? It's like this Wigner surmise. I think you'll be very
exactly. That's right. Both of these things. That's right.
And so, but at large s, could you test that? Could you find an analog in gravity for that region, or that's not as interesting?
The likelihood of there being how to say, so in gravity, the energies at hand, the energies of black hole microstates, of course, they scale as 1 over the higher dimensional Newton constant.
Yeah.
And the energy levels that I think you might hope, the differences that you might hope to have access to in gravity are of order 1. So 1 power down by g Newton. And those are exponentially unlikely.
Mm-hmm.
So I think the thing that it seems to be more visible in gravity is long range repulsion, rather than imagining that there's some accident in the spectrum where there's the nearest neighbors are well separated.
Mm-hmm. Okay, thanks.
Mm-hmm. Right, so spectral form factor, what is spectral form factor? Spectral form factor is, we're used to the thermal partition function of some theory. In particular, we can take a holographic CFT on a sphere and heat it up to some finite temperature. That would give us Z of beta. The spectral form factor is, well, you take that and you add a bit of Lorenzian time evolution. That's what that is. But then you also do this. You have 2 copies, and the Lorenzian time of one interferes with the Lorenzian time of the other. You can call this thing Z of beta t. And if you plot it for some complicated Hamiltonian, what happens is that you normalize by partition function squared, then at 0 time you get 1. And I'm going to draw 2 things here. That. Okay, so, but actually would see is so I've drawn 2 curves here. One is what you would actually see for a complicated Hamiltonian. I've tried to suggest by the density of wiggles that it's a highly chaotic, oscillating, very non-universal function. However, if you do sort of a rolling time average, you integrate over little windows of time and average out, like we're used to seeing with COVID data lately, then you get a very smooth curve. That's what the blue curve was supposed to be on top of this. You get something very smooth. And the feature at hand, this long range eigenvalue repulsion, that corresponds to this long section where I really did mean that there's approximately linear growth in this spectral form factor. That is encoded by this. And this thing is called, colloquially, the ramp in the spectral form factor. And it sets in the sort of timescales involved are very long compared to your large N parameter. They're on the order, they are on the order of e to the n squared. But shorter than, maybe like a factor of 100, shorter than e to the n squared, but still very long. Now, so what I'm going to propose in the rest of the talk today is that there's some evidence that such a ramp in higher D gravity is encoded in Euclidean wormholes. And I should say before going on to do that, that there is some precedent for this. There's been a lot of recent work last few years on simple soluble models of low D quantum gravity. So for instance, Jacqui-Tiedeboim gravity, this two-dimensional model of dilaton gravity and its cousins, all of whom we now understand to be dual when they are consistent theories of gravity without requiring a stringy completion, that they're dual to random matrix theories, in which case, well, they have exactly this feature because random matrix theory has this feature. And it's encoded in gravity through an amplitude where one sums over wormholes. That's been understood extensively by many people, including Saad, Shenker, and Stanford in 2019. And more recently, there's evidence that, there's a computation that Jordan and I did last year in AdS3, where it's not, the status of AdS3 gravity is not clear at this time, whether it's a consistent theory of gravity or not, or if it's dual to something or not. But you can compute, what I'm saying here is you can compute a similar amplitude in JT and see that it also encodes a ramp in spectral form factor. And it's not at all clear that a priori whether or not these results in low D gravity are just their own thing. Low dimensional gravity has many features that do not qualitatively resemble higher dimensional gravity, most notably the absence of a graviton, of a propagating graviton. But we're going to follow this thread and see where it leads us.
So I have a question. So these curves that you are drawing, so these results that you are quoting, are they supposed to be independent of the dimension, or to be valid in a quantum mechanics, for a generic quantum mechanics?
Yeah. So the idea is these are true for a very large family of quantum mechanics, some of which come from lattice field theories. But the point is once you're down to quantum mechanics, then you're just talking about spectrum of Hamiltonian. And what the connection with n equals 4 and so on is that if we talk about n equals 4 on a sphere, say, or ABJM on a sphere, or what have you, then we are really just talking about some extremely complicated Hamiltonian with a discrete spectrum.
Okay. So there shouldn't be, essentially any dependence on the I mean, the details will depend on it, but the behavior should be the same.
That's right.
And but still, do we expect this is true for holographic models, or should be even more general for, I don't know, any field theory? I don't know.
Whether it's true for any field theory, I mean, I think the thing that you need in order to bring these techniques to bear is a large density of states in some regime. And large N CFTs give that to you. Holographic CFTs give that to you, because there's an enormous number of almost continuous black hole microstates. Is that true, for instance, in like a large N vector model? I don't think so. Just because the density of states isn't high enough.
Okay.
And there's a lot of operators, but their dimensions are still, well, so at least, or if we're talking about a weakly coupled large N theory, then the operator dimensions are too spread out. In general, they're too close to their free field values in order to form a very fine Dirac comb.
I see.
Sorry, can I also ask a question? I just wanted to make sure. So it's like the blue curve in the middle, that's the part of the random matrix theory, while a quantum system has the wiggly black null.
Yeah, it has the very wiggly fluctuating thing, yeah.
Okay. So while in this gravity theories like JT, I find the continuous one.
That's right.
Okay.
You don't find the fluctuations. And the reason, yeah.
Okay. Thanks.
There's two ways that you can get a smooth curve as opposed to a wiggly curve. I described that you can do a rolling time average. There's another way, which is you can imagine if you have a Hamiltonian, some fixed Hamiltonian, you can imagine taking an ensemble average around that Hamiltonian, where each eigenvalues, you consider an ensemble of Hamiltonians that are very close to a single one.
Mm-hmm.
This is what one is doing in random matrix theory, is you're averaging over Hamiltonians with a suitable distribution. And on average, the Hamiltonian will be the thing that you want, but there's some variance. And that is also enough to produce a completely smooth curve without fluctuations. And that's what you find in JT.
Mm-hmm.
And that's.
So, but if instead your quantum gravity would be dual to some concrete quantum mechanical model, you would expect to find the black wiggly.
Yeah, you'd expect to find the black thing. That's exactly right.
Thank you.
Okay, so better speed up. Hopefully this introduction, if nothing else, was useful. This is different knowledge than certainly what I was trained with as a young person. Okay, so the question is now, can we study Euclidean wormhole amplitudes in higher dimensional gravity? So, not 2, not 3. And, a priori, it's not at all clear that we can do this in any meaningful way. And the reason is say we want to consider a scenario where we have Euclidean gravity and we want to have a wormhole that smoothly connects like two boundaries, where the boundaries have the same topology as some black hole, like a spherical black hole in AdS. Well, in this case, where the boundary is positively curved and you're just completely generic, there's actually a theorem about Einstein gravity due to Witten and Yau, which states that there are no classical configurations of this sort. There's no solutions to the field equations with this topology and with these boundary conditions. So there's no solutions to the Einstein field equations of this sort. And so the wormhole amplitude, which is going to be integral over metrics of this sort divided by diff e to the minus Einstein-Hilbert action. Whether or not it exists or not is a question, but certainly it has no you might say, oh, well, maybe this is like an instanton, like we're used to in field theory, except it's not, because this amplitude has no saddle point approximation. There's nothing to expand around.
Sorry, Kristan. Do you know if this is also true for a zero curvature, so like flat space?
Yeah. So the Witten-Yau theorem applies when the boundary. You can look at the paper for the precise conditions in which it applies, but it applies when the boundary is flat or positively curved. and with no other sources for matter fields turned on.
Okay, thanks.
Let's go ahead. Also ask about the definition of this path integral. So, as you know, there's this conformal factor problem. So there's some way in which you need to define the contour of integration and so on. So the Split-Yao theorem, I don't know it in detail. Does it exclude all?
It's purely a classical analysis for which you don't have to define the path integral over the conformal mode.
No, yeah. So you look for solutions to the Einstein field equations. I understand that. So, but do they only consider real solutions, for example, or
they only consider real solutions.
Okay. So, but since this contour is might have to be somewhere through the complex plane, there might be some complex solution, or that is also, you don't think that's
the general, that's right. I mean, that's right. I think the problem is that it's not clear at this time, in what ways should one be allowed to study complex metrics, and in what ways is one forbidden from doing this.
Yeah,
the rules of the game are just not clear. So their approach, and our approach too in the talk today, is to try as much as possible to adhere to looking for saddles, or we're about to do some sort of generalized saddle, which is completely real, smooth, non-singular, and then worry about continuation of the conformal mode when looking at the spectrum of fluctuations.
Yeah, definitely makes sense. Okay, thanks.
It's sort of what you would do at one loop order. Okay, so there's no saddle point approximation for these things, and you might at that point understandably give up. But actually, there's a setting in field theory. There's settings in field theory where you run into similar problems, and you don't have to give up. It might, in particular, there's this literature dating back to the early 80s due to Affleck, and for instance, Affleck, Dine, and Seiberg. About instantons in 40 Yang mills in a Higgs phase. In the original paper of Affleck, this was literally just Yang mills with the Higgs field where there's a bet with the usual Mexican half potential in the VEV. And Affleck, Dine, Seiberg, it was in the context of n equals nf minus 1 super QCD out on the moduli space of vacua theory. And the thing is that in those cases where there's a Higgs VEV, whether coming from part of one of the super multiplets or just an extra scalar field coupled into the theory, in either case, in a Higgs phase, there is no such thing as an instanton solution per se. You can prove this. There are no instanton solutions to the field equations. But there's still the physics of instantons. If you were to zoom in on distance scales much smaller than the inverse Higgs VEV, then you would see, okay, well, yeah, there's the usual instantons. The thing is that the instanton is no longer an exact solution. It's only an approximate solution to the field equations. And there's some method to deal with this that goes by the name of the method of constrained instantons. And Jordan and I wrote a paper last October where we started to adapt this method to Einstein gravity, and we're able to start finding wormhole configurations that were in some sense important off-shell configurations of Einstein gravity. What I'm going to describe in my time today is a refinement of that idea, actually. That's I think under even better control. And it relies on the gauge fixing apparatus of gravity. So, gravity is, at least, in the loop expansion is a gauge theory. We have to divide by diffeomorphisms. And so, even classically, we have to fix a gauge in order to make sense of what we're doing. And something that one can do for a problem like this, where you're interested in geometries like this that are topologically basically something, in this case sphere, circle times sphere, and then with another direction, is we can fix globally something called, if we were doing a differential geometry class, we could call these Gaussian normal coordinates. But in the context of AdS CFT, this extra direction along the wormhole, well, we can call that rho, can fix something called the radial gauge, which is analogous to Pfefferman-Graham that you may be used to from working in AdS. What we're going to do is we're going to separate the coordinates at hand into a radial coordinate and everything else. And we're going to fix that the metric is d rho squared plus stuff that has no leg along the radial direction. We could have fixed any other gauge too, but this is a convenient one for us. This is just an example. You have to fix a gauge. This is a convenient one to pick. And of course, the way that one does this is the whole Fadeev-Popov machinery. You introduce auxiliary fields to enforce the gauge fixing condition, and then there's also ghosts. So you have the Einstein-Hilbert action plus auxiliary fields times the gauge fixing condition, and write that out there, plus ghosts. And the thing is that, well, if we integrated out the auxiliary fields and we enforce the gauge fixing condition, then we're no longer free to vary those components of the metric in the gauge fix theory. We're no longer free to fix the components of the metric that are fixed by the gauge choice. Alternatively, if we think about not having integrated out the auxiliary fields yet, the field equations of the gauge fix theory have a right-hand side, well, compared to the usual Einstein's equations. So EOMs of the gauge fix theory are R mu nu minus R over 2 G mu nu, the usual Einstein field equations, equal to 16 pi G times an I times a lambda mu delta nu rho in this gauge choice. Oh, and maybe this is an 8 or something, but you get a right-hand side due to the auxiliary field. You get an effective stress tensor. And normally, we just consider configurations where the right-hand side is 0, the auxiliary field is just 0. But if we were doing field theory, like real field theory, then we would integrate over all configurations subject to the boundary conditions, including ones where the auxiliary fields can pick up a VEV. That's something that we would do if we were doing quantum field theory. It's just automatically there as part of the full path integral. And so you might wonder, well, does something like this have a place in gravity? And well, we're arguing yes, it does, and indeed you can find wormhole configurations this way. I should also say too that I invoked this method of constrained instantons before. One can revisit the old papers on method of constrained instantons and it looks like, this is work in progress, but it looks like those old papers can be understood in exactly this kind of language that I'm describing here, where there's you don't have an exact instanton, but you have a solution that is supported by the gauge fixing apparatus. So with this particular gauge choice, we can find wormhole solutions. So you can think of them as new solutions to the field equations of the gauge fixed theory. And in this radial gauge, what do they look like? Well, if we're talking about S1, let's talk about something with S1 times S3 boundary in AdS5, just to give something very concrete to talk about. You get a family of configurations that look like this, d rho squared. I'm just going to write out the line element real quick. There's the line element, where tau is a circle and d omega 3 squared is a sphere. And this configuration is labeled by parameters b, which, okay, we'll come to that in a second, b, and then beta 1 and beta 2. And in the spirit of pictures worth some large number of words, what is this thing? Well, this is a wormhole, if you stare at it for a little bit, where rho goes to plus infinity over here and minus infinity over here. And so there's two asymptotic regions at large positive rho and large negative rho, and they're smoothly connected through the middle. There's a bottleneck whose size is parametrically b to the 4. So b is a bottleneck size. And what are beta 1 and beta 2? They're the sizes of the circles out at infinity in units, where the sphere goes to unit size out at infinity. And well, there's a family of these configurations. B is like a pseudo-modulus that labels these. And if we want to talk about smooth non-singular metrics, it has to be bigger than or equal to 1 in these units. Okay, so we can land on.
Kristan, can I ask a curiosity?
Yeah.
So if you go back to the JT example,
right.
So, correct me if I'm wrong, in that example also you don't have on-shelf wormholes.
That's right.
But okay, they are able to compute the path integral exactly, and so they consider the off-shell ones and they get the result. So if you apply these in that case,
you can redo their computation in this way with the same, I mean, you can even do it exactly.
I see. So you do find that this configuration give you the leading contribution in that case as well.
That's right. That's exactly right. So you can, this is, if you will, one way of saying this is a way you can reorganize the lower dimensional computations in a way that can be adapted to higher dimensional gravity.
I see. Okay.
I mean, the details, the fact that loops are completely soluble in low dimension, that there's no extra excitations and so on, like that's, that doesn't generalize. But this method for finding, if you will, that, well, this is what I was about to say, there's an integral representation for the amplitude that this tells you. And in JT, there's an integral representation as well. And sort of the fact that an integral representation exists and that it has some semi-classical expansion that's true both in JT and here, and you can, how do you even land on this? Well, this is something that this method gives you. So that.
Can I ask something else, please?
Yeah, hang on. Let me just write one equation and then.
Sure.
Yeah. So what you get from this is then that there's some integral. Basically, what you would do if you were doing a loop expansion is you would integrate over all possible allowed values of the pseudo-modulus with some suitable measure that comes from variations of B or variations of the metric. So there's the right measure on the space of those fluctuations. Something that comes from something called Wheeler-DeWitt metric. There was the minus the class e to the minus classical action of that wormhole, and then a one loop factor at fixed B, and then plus higher loop corrections. That's what you would get from this. If you tried, so the strategy then for evaluating the wormhole amplitude would be to say, look, let's take this fixed wormhole, this thing that solves the equations of the gauge fix theory, and imagine doing a loop expansion around it to whatever order that you want. Presumably needing the details of string theory at some point, and then but then there's an integral over the bottleneck size that one has to perform at the end, because there are contributions to this amplitude consistent with boundary conditions for any bottleneck size as long as the metric is smooth and non-singular. Okay, with that out of the way, what was the question?
Right. So I'm missing something before. How do you know what kind of boundary condition to put for the auxiliary fields, for example? How to treat the auxiliary fields?
Right. So good question. I mean, the boundary conditions that we want to impose for the auxiliary fields are that they act, that they provide a representation of delta function in the path integral, and that in such a way that is consistent with the boundary condition that we impose, the boundary conditions that we impose on the metric fluctuations. So the metric fluctuations, are anchored down at infinity by boundary conditions, but then they're allowed to fluctuate. And what we need for the auxiliary fields for their, they need to act as delta functions for those fluctuations near the boundary.
Okay, thanks.
Yeah. Okay. We can compute the action, the classical action of these wormholes. The one loop factor is beyond us at this time. The one loop factor is computable in two-dimensional gravity and in three-dimensional gravity, but not in general. And the action, it turns out it's very nice to reorganize the data here according to the energy that you would see on the boundary according to the usual holographic dictionary. So the energy that one has is goes as, in this case, b to the 4 over g. And if you convert from b, this bottleneck size, to energy, what you would see is, so this wormhole amplitude, you can write it as an integral over energies where there's a minimum value. You go up into the sky. And the classical action piece is actually very simple. It's just a Boltzmann factor, it turns out, but with two betas, because this geometry, there's two betas, one on each boundary. And then there's, a one loop factor that, as I said, is beyond us, plus loop corrections. And okay, two observations about this. Well, I mean, it's great that we can even get to this point. But there's two features here that I want to draw out. One is that the energies that one integrates over, this thing I'm calling E naught up to the sky, E naught, it turns out, is the threshold energy of it's the energy of the lightest black hole in AdS with spherical boundary, so-called small black holes in AdS. You know, it's this. This is true independent of the renormalization scheme. It's sort of according to a naive renormalization scheme. There's this like 3/8 that one finds, and you get exactly this. So somehow the energies that are supported by the wormhole, I have in mind, I'm doing the simplest thing where the wormhole carries no macroscopic angular momentum, just energy. The allowed energies are precisely those of black holes in AdS with the same boundary topology. That's not at all obvious why that should be the case. That's an empirical fact about the wormhole in AdS 5. In AdS 3, there's a more refined version of this where we know how to look at wormholes that carry angular momentum as well as energy. And in that case, the spectrum of energies carried by the wormhole at fixed spin exactly coincides with the spectrum of energies of black hole microstates of black holes with the same fixed spin. So this is one connection already off the bat that's telling us that there's some connection between the wormhole and the black hole. The second is that the wormhole solution that I wrote up above, it's not obvious from the way that I wrote it down, but this is actually this is a particular analytic continuation of a black hole in Euclidean AdS 5. So the wormhole metric is the analytic continuation of black hole in AdS. And the way that the analytic continuation works is that if you set beta 1 equal to minus beta 2 equal to some size beta, and actually you get the Euclidean black hole. Although, you know, you need to do one extra step to get the black hole, really, because you need to impose Euclidean regularity at the horizon. So that fixes, like, what is B? B is roughly the mass of the black hole. B to the 4 is the mass of the black hole. So you have to fix B in terms of beta to have a regular solution. So this is the analytic continuation of the black hole.
Sorry, but you don't have two boundaries, no? Well, but
yeah, this is what I'm saying. If you take the thing with two boundaries and you substitute in this,
yes,
and you then fix, choose that the parameters are such that the Euclidean, then that basically it chops the wormhole in half. If you,
so why is that?
Let me plot this. If you make that choice, this factor up here, if you stare at the tau component, the tau component, the circle shrinks to 0 size at rho equals 0.
Oh, I see.
And so if you can, then it's a cigar, and then if you impose regularity, then it is just the black hole.
I see.
So in other words, you can go from the black hole is the continuation of the wormhole. The other way around, I don't know how to go there, but
so in a sense, for a special choice, the wormhole breaks into two black holes somehow.
That's right. That's right.
That doesn't look very smooth, right? When you, I'm confused. So, is it that your wormhole is pinching?
In that limit, yeah, it pinches.
Then it's but then the geometry at the pinch point's a cusp, not some kind of smooth,
That's right. But this is the usual. It's the usual kind of cusp in IML. It's the usual cusp in the cigar if the black hole mass and the temperature are not matched correctly.
Ah, okay.
Okay. The third observation, though, to draw out is that because of the Boltzmann factor, And the fact that the thing multiplying it, the effective like density of states in this integral is coming from one loop effects. This integral is necessarily dominated by small energies, not macroscopic ones. Macroscopic black wormholes correspond to energies of order 1/g, and those are very much suppressed here. So this wormhole amplitude is really dominated by Planckian effects, things that are well outside the semi-classical effective field theory regime of Einstein gravity. And so, okay, what can we do? I'll end with this because my time is I'm already past 5 minutes. I'll leave with this comment. There is a solution to this. There's a way basically to extract semi-classical physics reliably from the full wormhole amplitude. The full wormhole amplitude, what this last point means is that it's UV sensitive. So beyond even the fact that we don't know how to compute these loop factors, the whole amplitude is really a UV sensitive object. It probably only makes sense in a proper theory of quantum gravity like string theory on AdS 5 times S5. However, there is an integral transform that we can perform that does have, that localizes to macroscopic wormholes and has a good semi-classical approximation. And what we can do basically is we can, if you think about this amplitude, it has 2 betas. And in statistical physics, we're used to being able to go back and forth between ensembles. You can look at fixed beta, which means fixed temperature, or you can look at fixed energy, which is microcanonical ensemble. And the relation between the two is, Lagrange transform and inverse Lagrange. So there's a transform to what I'm going to call microcanonical with quotes, where where one fixes the energies on each boundary rather than beta 1 and beta 2. So in other words, you actually integrate over beta 1 and beta 2. And the reason why I put the quotes around microcanonical is the way I can do this sensibly, I need to introduce a little window, like what one usually does in statistical physics as well. You usually don't talk about microcanonical ensemble per se, but you fix like there to be a little window around some fixed energy. So with a resolution window, delta, which I have to have it scale as g Newton to some power, like square root g Newton, for instance. And if we do that, then there is a semi-classical saddle point for all parameters. Where beta 1, beta 2, which now I'm allowing to vary, and even the bulk fields and also the energy carried by the wormhole have some saddle point values. And if you go through this, the geometry that you end up landing on is one where beta 1 is purely imaginary. Beta 2 is purely imaginary, where the energy is the average energy that one fixes on the 2 boundaries. And then what I have in mind here is that E1 minus E2 is very small. So you study energies on the 2 boundaries that are basically the same. And what do you get for the configuration of fields? Well, it's the wormhole analytically continue to these values. And the geometry that one gets from this is something that has appeared in the literature before, although it wasn't quite clear what to do with it at the time. This is the double cone of Saad, Shenker, and Stanford from 2018. And right, so, okay, so where I've gotten to this stage, I should stop now. So let me just say where we've gotten is we've gotten to the point where we can set up a semi-classical expansion for wormhole amplitudes and higher dimensional AdS gravity. Those methods can be adapted. We did in our paper as well to full-fledged AdS CFT. And we've seen that, you know, they lead to, as if you impose sort of different boundary conditions than we're used to in gravity, where you fix energies instead of circle sizes, betas, that you can find saddle point approximations for these wormholes. And they're given by something that was written down before, but it wasn't clear what to do with this double cone. If I had more time, I would say how this is connected to level repulsion, the thing that we started with, so it wouldn't have that this is encoding something physical, as well as talk about some of the problems that come then if these geometries are really contributing in string theory, this factorization paradox. But I'll end here. So thank you very much. Especially for not yelling at me as I went a few minutes over. Sorry about that. Thank you.
Okay, let's thank Kristan for the great talk. And do you have time for a couple of questions, or do you?
Yeah, absolutely.
Okay.
Can I ask a question? Oh, sorry.
No, go on.
So at this point, you are landing on some complex metric, I guess, because beta is imaginary and the fields are a suitable continuation and so on.
It's actually, it's real, but it's Lorenzian signature.
Okay.
Let me write it out. What you get is minus well, actually, let me not do the so it's actually a Lorenzian signature metric. What it looks like is something like this, maybe better drawn. And what it is it's an orbifold of the two-sided black hole in Lorenzian signature, where one orbifolds by translation along time, by Lorenzian time, because here tau is time.
But so yeah, so this my question was, is this solution actually a solution of the original equations of motion, or you still need to do this constrained thing?
It is actually. So this particular configuration is a solution because it's an orbifold of a solution. It is a solution. And without having to introduce this funny business with the gauge fixing. And if you will, but the thing is that, how to say, if you didn't do the gauge fixing, blah, 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 then how to say, this is a solution where the size of the two circles on the two boundaries is coordinated, it's the same.
Mm-hmm.
And to really say that you have a saddle point, so there's actually a family of these configurations for any t, which you can fix by a boundary condition, but also for any b, the sort of mass of the black hole that one is starting with. And because of that, if you just, when these guys wrote down these geometries, these orbifolds, if you will, the mass of the black hole is a modula, an exact modulus at tree level. And to say that you have a, you want to stabilize that modulus, you want to fix it. And the thing is that that's what this, if you will, one way of packaging our results is that by going to Euclidean signature, by carefully thinking about the amplitude, doing this gauge fixing and all that, that allows you to stabilize the B modulus, or the energy of the wormhole.
Okay. I guess some.
Yeah.
So can I ask you one thing?
Mm-hmm.
So how do you know that there are no other settlers that cancel these contributions? So
we don't.
Yeah, I was a bit worried about that because, say I take the product of two partition functions, no?
Right.
And then I can also write it in a weird way in which they interact, but they really don't. No, I just put some deltas or something like this.
Right.
And then I find configurations like wormholes and things that have to cancel them. No, so
this is what you're asking about. Just for this maybe something that most people in the audience know, but this is this thing about I was alluding to with factorization paradox, which is that these geometries, in a picture, these geometries are contributing to the two boundary problem in AdS, which if we were to represent that as a sum over geometries, you would include disconnected contributions plus connected. And in terms of CFT, AdS CFT, you would say, look, if the boundaries here are M1 and M2, you would want to say that the sum over geometries with two boundaries is dual CFT partition function on the union M1, M2, which is this, except for conformal field theory, local conformal field theory, partition function factorizes. And therefore, those extra contributions, the connected things, better add up exactly to 0. Except here we have a saddle point, an exotic saddle point, but still a saddle point contribution to the connected part. So one expects that if we want to talk about the dual description of n equals 4 on the nose, that there's some other contributions in gravity that should somehow exactly cancel the wormhole. And the thing is it's unknown at this time what those contributions would be. I mean, the sort of approach for this sort of potential problem with AdS CFT was pointed out already almost 20 years ago by Navicena and Mals, and sort of was in the air as far as I can tell in discussions at the Institute at the time. The Witt and Yao paper was just before this, actually, just before their work. And it's been known for a while, but you might wonder, okay, well, maybe all these things just don't contribute to path integral of string theory, blah, 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 string field theory on these spaces. But the recent, I guess the thing is about these wormholes, what I was saying at the beginning of the talk is that they seem to encode something that's physically very sensible, namely level repulsion, which has made the story more complicated. Like, they really do appear to be there if one, or at least there doesn't seem to be a good reason to exclude these contributions from the sum over metrics. And they seem to encode something physical. So what gives exactly? I think it's not known. You might say, okay, well, maybe there's some additional, maybe even non-geometric contributions to the two boundary problem in string theory that restore factorization. But we don't know what they are at this time. We don't know if higher topologies can also interfere in such a way as to destroy this contribution. It's an ongoing line of research.
Yeah, I see. But it's very nice that you can find at least these guys in other dimensions. That's not trivial.
Yeah.
Sorry, can I also ask something? Probably you explained it, but I missed something. So how come you can find, so naively I would have thought that if I find a solution after gauge fixing, that solution existed also before, but it seemed, if I understood what you said,
it's because of the thing that the gauge fixing auxiliary fields pick up of a background. That's what prevents the, how to say,
the uplift to
to a full solution of all the equations in motion. In other words, one way of saying it is that, you know, these geometries have this right-hand side of gauge fixed field equations, not zero. Right.
But is there a sense in which these are approximate solutions, or I don't know?
Yeah, they how to say, you know, there's another perspective on these things that we can think of them as constrained instantons. That was actually how we found these geometries originally. And then we realized that there was this other kind of technique where we didn't have to. So constrained instanton is basically you slice up the space of fields according to a constraint, you foliate it into, you know, some function equals constant slices, and then you extremize first on the slice and then integrate over the slices at the end. It's just, and you know, there's a huge, you can do that in principle as long as you do it right. You can do it any way that you want, as long as you do it correctly. There was, and therefore, you know, if one's going to do that, one should choose an efficacious choice. And we found some efficacious choice, but that approach, how to say, it's also sort of annoying at loop level to make sense of it. This is a much easier at loop level to make sense of. A very natural question, though, is since one is relying on the gauge fixing apparatus, as to what extent is what you're doing gauge invariant? It's hard to compute it's hard to perform many explicit tests here, but what seems to be true is that, you know, these wormhole amplitudes are really integrals. And the integrand, as far as we can tell, is not gauge invariant. Only the integral is. So if you pick, you know, we can pick other gauge fixing conditions, and they're, you know, like a transverse gauge or some such. And in that case, we can find wormhole solutions as well to the gauge fixed field equations. They look different. They're different metrics, actually. They're different spacetimes. But the thing that, you know, the amplitude is the thing that should be gauge invariant. So you can represent an amplitude in any number of integral ways, and the integrand need not be gauge invariant, but the whole thing has to be gauge invariant. The thing that we're saying at the end, though, about this connection with double cone and so on and so forth, that is because one is taking the full amplitude and one is performing some transform. That is a gauge invariant statement.
I see. Thanks.
Okay. Can I ask you another quick question? Can you somehow interpret your construction? You had this fact of the analytic continuation to the black holes, not the single black holes. So like in lower dimensions, these wormholes, you can kind of slice them in the middle and put a complete set of states, no? And they look like, you know, two black holes with some all two defects, no?
Yes.
It's something similar here, probably, even though you don't know what is the Hilbert space, because no?
Yeah, in principle, should yes. I don't know how to do this very concretely yet, but yes.
I see. Okay, thanks.
Unfortunately, I've reached my UV cutoff as well.
Yeah, don't worry. So let's thank Kristan again for the very nice talk.
Thank you.
And
thank you so much for having me.